Hi guys, Dr. Diaz here again. First I'm going to write here some useful formulas that can be used for lens and mirrors, and one of those is the focal length, which we already discussed this one. If you remember the equation for the focal length, we got something like this. One that says 1 over the focal length is equal to 1 over s, which is the distance from the object to the mirror, or in this case of the lens, and s prime, which is the distance of the image to the mirror or lens. And we can rearrange this one, change it a little bit, and write it like this: f is equal to s prime divided by s plus s prime. Another equation that will be useful is when you're trying to find magnification, and that one says magnification. Alright, remember this one's for focal length. Let's put here focal length. This one's for magnification, that it says m is equal to, something is written like this, minus s prime divided by s, or sometimes they use q and p, where q is the distance of the image to the mirror and p is the distance of the object to the mirror. And sometimes they use another type of equation, which is the one in terms of height. It could be also written as magnification is equal to, actually they use capital M for magnification, sorry about that, let me change this, h prime divided by h, which is h prime is the height of the image and h is the height of the object. And you know, sometimes you might have an equation that it would be useful when you're only working in terms of the distance and the height. Yeah, this also, you're combining these two, this also helps a little bit to find or the height of an object. Oh, sorry about that, it was actually h. So the equation is s prime divided by s is equal to h prime divided by s, which sometimes is useful to find the height of the image or the height of the object, or the distance where the image is from the mirror lens, or the distance of the object. So this, I mean, you can use these equations that are very useful too. Oh, and the negative sign here in magnification, what it means is the image is inverted. Oh, and the other equation that sometimes is useful is, you remember the center of curvature, which is always 2 times the focus, which means that the focus is equal to the center of curvature divided by 2. Now we're going to our discussions of converging and diverging lens. So I'm going to write here a diagram. Voila, and actually here's the diagram. And this is a case of convex lens in which the object is far away from the focus. And look what happened. Here's the focal point, or the near focal point that I had to call. And because this is the lens, look, if the image, I mean the object is here, you would expect, if you're looking, I mean, depends on which direction you're looking, the images are going to appear the other side of the lens, right? It's not like in the mirror, so you expect them to be real, be in the same side where is the object. Well, if you use glasses, you know that your image, your eyes is one side, the glasses is in the middle, and the object is far away from you. All images actually form inside the corner of your eye. If that makes sense. Later on, I'm going to show you some diagrams how this works. So what I'm trying to say is that this object, I mean this object is here, this is a pine tree, and the image is here, and this image is real because you expect them to see the other side of the lens. In mirrors, you expect them to see in the same side of the object. In lens, of course, you have to see the other side, otherwise you're not going to see the object. I mean, it's reflected, it's actually difficult to see. Okay, so, and look what it happens. A ray that it goes parallel to the optical axis, when it goes to hit the mirror, it will go to the focus. You would say in the case of converging, well, in the case of converging, it will go to the focus here, this point, in this focal point, right? It has like 2 focus, the near one and the far one. So, because the object is going to, I mean, the image is going to form this far away from the focal length. Well, a ray that it goes parallel to the optical axis, when it hit here, it will converge and go to the focus, and it keep going all the way to infinity. And then you can say one that it goes exactly to the focus, right? When it hit the mirror, it will go parallel to the optical axis. You know, this ray here and this ray here are the 2 rays that you usually were working with. But there's a third one that I mentioned, the one that it goes exactly at the center here. Well, this one, it will keep going, and you can see that this ray, this ray could come here, and this ray, which is the three rays that we always talking about, they all converge at the same point where the image is going to be formed. And here in this case, the image is real. You can read here, is real, is downward, and it's actually smaller. Sort of, yeah. So those will be the characteristics. Let me show you another type of lens here before we start solving some of these problems. Yeah, I hope this example that I put here helps a little bit. But look here, all these 4 cases. This is a lens, this is a convergent lens, this is a divergent lens. This is a concave mirror, and this is the divergent, let's say convex mirror. So here, if you remember what we said a moment ago, which is actually similar to the case we were seeing a moment ago here, when a ray goes parallel to the optical axis, it hit there, go to the focus. When one goes exactly to the center, keep going all the way without diverging. When it goes to the focus, it hit the mirror, goes parallel to the optical axis, and all 3 points converge at the same point. For lens, we know this image is real and is downward, and it seems to be smaller. Now, what happened in the case of, this is the case we're talking about real image. You can read here, real image. In the case of lens, you remember all those analyses we did. A ray that goes parallel to the optical axis, when it hit the mirror, will go to the focus. The ray that goes through the focus, well, it hit the mirror, will go parallel to the optical axis, and one that goes exactly to the center, it would hit back and it will go there, and you can see that all 3 rays converge at the same point, right? All 3 rays converge at the same point, which means that the image is going to form here is real, is downward, and is smaller. Now look at this one for the converging lens. This is when the image form is virtual. If you remember, for lens, here form on the other side of the lens is real, but what it form the same side that is the object, that is a virtual one. So here we go, a ray that goes parallel to the optical axis, when it hit here, it seems to go to the focus here, or it diverges the other side, but it seems to go in this direction, right? Like in the case of these mirror. And one that it goes exactly to the center curvature, it doesn't, it bounces back, it goes in the same line, and you can see where these 2 lines converge. You can take the other one that it supposedly goes to the focus, and it will go parallel to the optical axis, but moving backward, all 3 rays will converge at this point. Here the image is formed, is upward, is smaller, and is virtual. And in this case, we discussed this one last video, when the image is between the focal length and the, well, actually in this case it's not the focal length, this is a convex mirror. Well, here is, well, here we go. Yes, the other case I was saying it was a converging mirror. But here we go. A ray that goes parallel to the optical axis, when it hit the object, it will bounce off, but then if you go in the other direction, it will go the direction that is the focal, right? And then one that it goes exactly to the center, it will bounce back, but if you go backward, there where those 2 rays converge, we studied this one in the previous video, that's where the image is going to form. In this case, it's upward and is virtual. That is smaller than the actual side. Now, let me see if we have another one to show you here. Okay, now we have here as well, this one on the right is a similar case that we discussed here. You can see the ray going here, bounce off, but it goes to the focus. Another ray going here, looking at the focus, it goes parallel to the optical axis. When it goes back, when they're in converge, there is where the image is formed. Now look at this one here, because this actually is a converging lens. Well, in this one is the object is between the focus and the lens. Between the focus and the lens. What happened? It goes here, bounce off, so we're looking for the focal point, and it goes all the way there. Go from the focus, hit here, goes parallel to the optical axis, but it will go back. Here's where both form, and look at what happened with the image. It's bigger, it's virtual because it's forming the same side of the object, and it's upward. Okay, let me show you one case. And in this case, guys, look, it's the 3 type of eye problems and why people use glasses, because they have myopia, hyperopia, whatever it's called, and astigmatism. Well, look at here. For the first one, what happened here? This is the hyperopia, whatever it's called. Sorry about that. look, the ray is a far-sighted kind of problem. And look, the rays converge basically inside the cornea of the eye. Right? This is the eye. I mean, this is the retina. The cornea is here. I'm sorry about that. The retina is here. It's hitting at the back a little bit far away. So in order to correct this, you need a convergent lens. That's why you put a convergent lens, and then voila, there, hitting exactly where the image is always going to form. This case, what happened? The image, which is myopia, the image is forming. This is the near-sighted problem. It's forming closer. So in this case, you would need a convergent closer. You need a divergent lens. So this move the image to be formed here at the retina, which is this case. The case of astigmatism is actually a little bit more complicated because it seems like you need a cylindrical kind of lens in order to work. Now let's go back to the eye, and finally here we have the eye. What I was saying, the lens, the iris. Here the retina, and here in the retina is where the image always is formed, and you can see that the image you can see in the back of your eye, in the retina, is actually upside down. The tree you look at straight, and it's going to be in your eyes upside down. So everything you see in the back of your eye and your cornea is going to be upside down. Okay, guys, I hope this helped a little bit. Just check these. Actually, they're taken from the PowerPoint, and read a little bit about eyes and how the images are formed and everything. Okay, take care, guys. I will solve problems in a second. Bye.